Hi, my name is Yuri Tiagi, and in this video, I'll be going over fluids, Unit 8, which you will need to know for the AP Physics 1 exam. Before I get started, I first want to congratulate you all who took the AP Physics AP Calculus BC or AB exam today. I know you guys all did great, and don't worry about the score. I know you guys all did fantastic. Okay, so fluids. Let's start with the basics. First, we know the density equals mass over volume. So the symbol for physics and density is rho, spelled PHO, sorry, RHO, and that's density equals mass over volume. Next formula we need to know is that pressure is equal to the perpendicular force divided by the area. So an example, the pressure of your finger pushing down something is equal to the force you apply divided by the area of the tip of your finger. That's pressure. Pressure in a fluid. So let's imagine we have a fluid, a tank, right? And we have a string connected to a flat piece of metal. Okay? So if we think about the pressure that's acting on the fluid, we can think that there's a column of water above this fluid. We can imagine a column of water above this fluid, right? That's pushing down on this piece of metal. So the force of the water column is equal to the mass of the water times gravity. The mass of the water we can also describe using, this is a common thing we do with fluids, as density of water times the volume of water times gravity. Because again, remember, density equals mass times volume. So if I multiply volume, mass is equal density times volume. So we have that, and we know that the volume of water, if we call the sides, call the piece of sheet metal, it's a rectangle with a width and a length, and the string is a height h. So we know this column of water has a volume, length times width times height, of LWH. So this is equal to density of water times LWH times G. From our formula, pressure equals force over area. So our pressure from the water, or from the fluid, pressure of fluid PF, is equal to the force. So the force is this. So density of water times LWHG divided by the area. The area is LW, right? So LW. So our final answer is that the pressure from the fluid, or on this object, is equal to the density of the fluid. I changed water to fluid just to make it more universal, times the height times gravity. And this is gauge pressure. And it tells us, basically what this formula tells us, is that in a fluid, no matter the shape of the fluid, no matter like how the container is shaped, the pressure that an object feels is solely based on the height the object is in. So if we have a container like this, right, and we have an object here, or if we have a container that's like, I don't know, this, and we have an object at the same height, these two objects both feel the same amount of pressure because they're both the same height away from the surface. In our formula, gauge pressure tells us that that's the pressure you feel based on the height. Next, so that's gauge pressure, right? Absolute pressure is equal to the pressure of the atmosphere plus gauge pressure, which is PFHG. Or it looks a little better if I do PFGH. That's the way you write it usually. Oops. And again, the reason why this is a absolute pressure is because in our example here, we didn't account for the pressure of the atmosphere, right? But the atmosphere, the air molecules, also have a pressure on the fluid, which adds to our total pressure on the object. And that's the formula for the absolute or total pressure. Okay, next. If we imagine another object submerged, like so, we can think that the pressure, right, based on our previous formula, here is going to be less, the pressure at the top is going to be less than the pressure at the bottom, because the pressure at the bottom is a greater height than the pressure at the top. Therefore, this bottom pressure is going to be greater. Because the bottom pressure is greater, pressure is force over area, we're going to be having an upward buoyancy force, and they call it FB. And the reason why there's no buoyancy force on the sides is because they're both the same depth, right? Like the side here, they're all of the same depth, same area, same force. Therefore, there's no pressure on the sides. So our formula for buoyancy, so we know buoyancy is always upwards because again, the pressure difference from top and bottom. So the buoyancy force is equal to the density of the fluid times the volume submerged times gravity. So this tells us, basically, if you're looking, that density of fluid times volume submerged, that's equal to the mass of water displaced times gravity. And what this tells us is that the buoyancy force is equal to the weight of the displaced fluid. Okay, and this is called Archimedes' principle. And so the idea is let's imagine that this is a mass mg, right? So we call this density of object times volume of object times gravity, and we can call this buoyancy force density of fluid times volume, actually not volume of object, volume submerged times gravity, right? This gives us mg, this gives us mg of the water. So in order to float, we need this to be greater. Therefore, floating only happens when the density of fluid is greater than the density of the object, based on the force for buoyancy. Okay, so let's try a quick problem with buoyancy. Let's say that we have a beach ball in the water, and a guy is pushing the ball down. Okay, and so the mass of the ball is 0.5 kg. The volume is 2.5 times 10 to the negative 2, and we're looking for the force of the hand. So we're looking for FH, and we know that the balloon or the ball is not accelerating, it's staying there just in the water, so it's constant. So whenever we're doing a problem like this, it's always helpful to first start with a free body diagram. So from our diagram, we see that there's a FB, force of buoyancy upwards, because again, it's always upwards, a force of gravity from the ball, and a force from the hand. So writing an equation, we know sum of the force is 0 because it's not accelerating. The ball is just stationary. So force buoyancy equals force gravity, force hand. So buoyancy force we know is density of fluid. So density of water is 1,000 kilograms per meter cubed. The volume submerged is right here, 2.5 times 10 to the negative 2, so 100. And gravity is just 10. And this equals to the force of gravity, which is 0.5 times 10, which is 50, plus force of hand. And from here, we can just solve for force of hand, and we'll get 100, so 250, minus 5. Force of hand is 245 newtons. So again, the process for these types of problems, free body diagram, sum the forces, and then use the formula to figure out whatever you're looking for. Next. So the last formula we need to know for static fluids is that if we're applying a pressure, let's say we have a system like this, right? And we apply a pressure here, it's a fluid, right? We apply a pressure onto the fluid here, call this pressure 1. Then Pascal's law, which states force 1 over area 1 equals force 2 over area 2, states that because we're applying pressure here, P1, there has to be an equal pressure applied to the fluid here, called this P2. And so Pascal's law, basically that's what it says, right? It says P1 equals P2, and if we use the formula for pressure, we get that F1 over A1 equals F2 over A2. And so this is helpful for describing the motion of real-world objects like hydraulic presses and things that use this concept of force and area. It's like mechanical advantage, but using water. So that's Pascal's principle, which you will also need to know for the exam. And the last thing that we need to know for fluids is moving fluids, right? So the stuff I was talking before is all for static fluids. These are all the stuff you need to know for moving fluids. So the first thing you need to know is that let's say we have a tube here, right? And the tube expands like so. And this tube is filled with water, right? So we say that this has a area 1 here, area 2 here, and let's say it has velocity 2 here, and a velocity 1 here. So what the continuity equation says is that area 1 times velocity 1 is equal to area 2 times velocity 2. So this area times velocity business, what it means is a flow rate. It tells us how fast liquid is flowing through a certain area in a given amount of time. And so it's saying that the velocity here times the area there is equal to the velocity here times the area here, which makes some intuitive sense, right? If we have a pipe and we have a fluid flowing through it, the fluid, it has to be the same amount of fluid here and here based on mass conservation. And so because of that, the flow rate has to be the same here and here because, again, the conservation of mass, we have to have mass dispersed throughout the system, and therefore this equation holds true. And finally, the last equation you need to know for moving fluids is Bernoulli's equation. So let's imagine we have a pipe and it's going like uphill, like so. And here we have a pressure, we have a velocity too, right? And here we have another pressure and we have another velocity too. And there's also a height difference, right? Call this H1 here, call this H2 here. So what Bernoulli's equation states is that the pressure plus the density of the fluid, density, again, Bernoulli's equation assumes the density is constant. So pressure plus the density times gravity times H1 plus the density times velocity 1 squared over 2 is equal to pressure plus density times gravity times height 2 plus density velocity 2 squared over 2. And so this, you might see, kind of looks a little bit like an energy equation. We have a gravity term, we have a kinetic term. I guess you could call this maybe a external work term. But yeah, it does look like an energy equation because it, in reality, is a type of energy equation. You don't need to know that, but that's the equation you need to know. And the important part about this equation is that sometimes when we're given a problem, we can use both these equations, right, together to find a value. So for an example, let's say that we had let's say for this problem, instead of this, we were given a tube here, went uphill, and it got bigger, like that, right? And we're given the radius 1, we're given the radius 2, and we're given maybe the change in height. And let's say we're also given let's say that's it, okay? So the change in pressure, let's say we're trying to find the change in pressure from here to here. So the change in pressure, delta P, is equal to, all these terms moves over. So we have H1, H2 based on delta H. So actually, let's move over. We have delta G times delta H. Sorry, negative delta pressure, right? Because I moved the pressure 1 minus pressure 2, which is negative delta pressure, plus density velocity 2 squared minus velocity 1 squared over 2. And so here we have delta H, right? we have density water, gravity, density, and we don't have V2 or V1. Let's say I messed up. Let's say we have a V1 here, okay? We do need a V1. So now we have a V1, right? But we don't have a V2. Well, we can use this flow rate equation, right? So we have the radius here, we have the radius here. We can find A1, A2, and we can find V2, and then we can find this, and we can solve our equation like so. So again, the idea is sometimes we have to use both equations in a single problem to figure out the final value. And two more things that are important with Bernoulli's equation. One, Bernoulli's equation, based on this formula, it tells us that fast-flowing liquids, fast-flowing equals low pressure, and slow equals high pressure. And so fluids, gases, all of those, they go from high pressure to low pressure. And that's the last thing you need to know for moving fluids. Fast flowing, low pressure, slow, high pressure, and fluids and gases go from high to low pressure. And so yeah, that's all you need to know for the AP Physics 1 exam on fluids. And yeah, that's it. Thank you guys all for watching, and I'll see you guys all tomorrow. Bye.